Hey there.
Hi.
How's it going?
Good. How are you?
I'm here.
Hanging in there.
I'm ready to be done with this madness.
I know.
Are you taking classes this summer?
Yeah, I just got into an anatomy and phys class for the summer.
Oh, good. Good,
Yeah.
good, good. Is it 185? Is that what you're taking?
Yeah.
Okay.
Yep.
Those are my good friends that teach it.
We have to order a lab kit and everything though for our house.
I know. In fact, I'm the one who I worked with them to get their lab kit. I teach a fully online chem and society class, and I've been using the lab kit for years, and it's great for a fully online class. And we talked about doing it for the second half of the semester, but it was going to cost the college $26,000 to do it for you guys, because we were going to get everybody like 2 or 3 labs at home.
Yeah.
So we just decided to do what you guys did for my class instead. And anyways, but for the summer, we've got time, and we got away with it this semester because you guys did half the labs at least. You had some hands-on experience, and so we were able to do that. But for the full semester, you've got to do some hands-on stuff. So yeah, we're all going to the kits for all the other classes too. So.
Yeah, they're having us buy it ourselves, they said.
I think maybe you're gonna get a fetal pig.
Oh, great.
You get to dissect on your kitchen table.
Just what I want to do at home.
Yes. Oh. Here come more people. Hi, ladies.
Hi. How are you tonight?
I'm good. How are you guys?
I'm good.
Let's give everybody a couple of minutes to get in here. Leah and I were just chatting. What's happening with you guys? Anything exciting? Nothing?
Oh, not too much.
You guys ready for the semester to be over?
Yes. Yeah.
Me too. Me too. Are you guys all going to take the last exam?
Yes. I am.
Okay.
I'm taking it.
Yeah.
Let me do my screen share, get that all set up. All right, I'm having some issues here. Come on. This chapter, you guys, isn't too long, so we won't be on the whole time. Although it's actually one of the more interesting chapters, I think. It's about nuclear chemistry.
Chapter 9 to be kind of hard.
Did you find it to be kind of hard, the acid-base stuff?
Yeah, it was hard.
There were a couple questions on the homework I didn't even get to answer because I was so confused.
Well, if you have questions, screenshot, because if I pull them up, it comes in a different order. So if you need me to answer something later, go back in and just send me a screenshot and I can explain it.
Okay.
Okay. Just because again, they're going to be on that last exam. So.
Yeah. All right.
Okay. Can you guys see my chapter 10? You good?
Yes.
Okay. Let me make sure we're recording because I had a problem recording last. Okay. Yeah, it's recording. Okay. All right. So we're going to start our look at nuclear chemistry with the idea of isotopes. And we've talked about isotopes, oh gosh, I think it was chapter 2. And the basics are this. For all the elements, there are different, I like to say kind of the everyday word would be form. There's different forms of them. So for instance, carbon actually comes in carbon 11, carbon 12, carbon 13, and carbon 14. And so if you had, I'll get to the slide there in a second. If you had a box with carbon in it, bunch of carbon atoms, okay? And give me a second here while I do my color coding. Let me see, blue. Okay, so you have a box of carbon atoms and you reach your hand in, whoops, you reach your hand in and you pull out an atom. The chances are that you're gonna pull out a carbon 12 atom. So a carbon that has a total mass of 12. When I say carbon 12, 12 is the mass. And so you can see in my little terrible drawing there, my white box, you can see all those white circles, those are carbon 12 atoms. But you may pull out a carbon 11, that's the yellow circle. You might also pull out a carbon 13, that's the green. Or you might pull out a carbon 14, 14, that's the blue. Now, I did the ratios skewed the way I did it. You know, you can see my box, and the majority is white. The majority are the carbon 12 because it is the most abundant of all of the forms, or what the actual term is, what's on here on the slide here, isotopes of carbon. But it does, like 1% of the time or less, come in carbon 13, carbon 14, or carbon 11. So the most common is 12, but it does exist with different mass numbers. It just depends on which isotope you have. They're all carbon because they all have the same atomic number. So when we talk about isotopes, I kind of like to talk about human beings. So, or even let's just talk about ourselves. We all have our own social security number. However, especially during the pandemic, your mass might be different. You know, what is on my driver's license, I'll tell you a secret, does not match what my real weight is. Okay, but at one time it did. One time it did. But my driver's license number or my social security number, you know, that's assigned to me. And it might be that I have a certain weight or a different weight, or, you know, whatever it is. And I don't, when I do that analogy, it makes it sound like it changes, like a carbon 12 might, you know, lose weight and become a carbon 11. And that's not really it. I use that analogy simply to say that it's the same thing. You know, I'm still me, or more of me or less of me, but carbon is still carbon. It's just that it comes in different forms, and the different form is what's called an isotope. Same element, so same atomic number, same social security number for all of us, but different mass. And for almost all of them, there tends to be one that's the most abundant or most common. So again, for carbon, that happens to be carbon 12. It also closely matches the atomic number, or excuse me, the atomic mass on the periodic table. And that's usually how you can guesstimate which isotope is the most common. That's not usually a question you get asked, but that's kind of how I know that. So again, if I stuck my hand inside this magical box and pulled out an atom, but I had to guess or bet, maybe I was going to bet $100 which one I'd pull out, carbon 12 is so abundant above all the other ones that I would bet, I'd probably even bet $1,000 that I'd pull out a carbon 12. Okay, the other ones are there, but the odds are very low that you're going to pull out of a whole box of carbon atoms, you're going to pull one of the others out. Okay, now going back to chapter 2 with subatomic particles, and that is protons, neutrons, and electrons, keeping in mind that the mass number, so for carbon here in this example, that's 12, mass is equal to protons plus neutrons. That's what sits inside the nucleus of an atom. Atomic number is equal to the number of protons. So again, carbon is always 6. If you change the number of protons, you change what you have. You might go to a nitrogen, or you might go to, you know, helium, or whatever it is. So atomic number stays the same, but it can have a different mass. This is the example on here, carbon 12. So carbon has 6 positive protons. Well, I have this written here. And then neutrons is mass minus number of protons. So mass 12 minus proton 6 equals 6 neutrons for this particular isotope of carbon. And I'll be honest, I can't remember. Yeah, I've got the other ones on this slide here. At least I have 3 of them. There is one more, but this one only shows the 3. That's fine. But I'm going to work it out for these 3. So if you can see, let me blow this up here. So this is carbon 12 right here, carbon 13, and carbon 14. And again, the reason that I'm using the mass number when I say that instead of the atomic number is because carbon is always 6. That's its atomic number, okay? It's carbon 12 when you're talking about a carbon atom with the mass of 12 or 13 or 14 or 11, because there is one with 11. And so if we talk about calculating the number of protons, the number of neutrons, and it didn't ask, but why not? What the heck? Let's also do electrons. Carbon is atomic number 6. So assuming it's a neutral atom, 6 positive protons and 6 negative electrons. And then neutrons is mass minus number, or mass minus protons, because they're one and the same. So 12 minus 6 is 6 neutrons for this one, 7 for this one, and help me out, you guys, what's the number of neutrons for carbon 14 going to be?
I'm going to say 8.
You're going to say 8, that's right. 14
Okay.
minus 6. Okay, so you basically just subtract the 2 to figure out how many neutrons. That's it. So for any isotope, you can do that calculation or determine subatomic particles. You've got to know the mass because they can be different. And then they don't always give you the atomic number. Again, they might just say carbon 12, carbon 13. That's because you go find what the atomic number for carbon is. It never changes. Use that for protons, and then subtract the mass given from the number of protons or from the atomic number, since they're one and the same. Okay, but we want to talk about radioactivity and nuclear chemistry. And I know most, if not all of you guys are going to go into medicine. And so depending on what you do, you may or may not do some nuclear medicine stuff, which is kind of interesting. When we talk about nuclear chemistry, when people hear the word nuclear, often they think of this word as well, right? Radioactive, or something's radioactive. Gosh, it's awful dangerous. Well, some isotopes are radioactive. They're unstable and they are spontaneously giving off energy, and that's where they become dangerous. And in doing so, we say that's a radioactive decay, which we'll get into that in just a second. But so you have reactants, these unstable radioactive isotopes of certain elements that on their own naturally spontaneously decay, giving off huge amounts of energy that can kill cells and do damage. But the other product, in addition to this crazy amount of energy, the product that results is a more stable and, let's say, safe isotope. So that radioactivity, the nuclear radiation that's emitted by that unstable radioactive isotope, as you can see there, I think this is kind of interesting. Of the known isotopes for all the elements, 264 are stable and 300 are naturally occurring and unstable. So probably the most common one, everybody's heard of uranium. Uranium is probably the most common radioactive isotope, okay? But there's lots of them, as you can see, 300 naturally occurring but are unstable. Even larger number of these isotopes are called artificial. Another word for artificial is synthetic, meaning they were man-made. So they were made in a lab. So we can actually make isotopes in labs, which is kind of crazy. All right, so let's talk about the types of radiation. We're going to talk about alpha, beta, positrons, and gamma. And we're going to start with alpha. Okay, this is the weakest. It's the least penetrating. Meaning you could stop an alpha particle, you could stop it from reaching your body by wearing clothes or even a piece of paper. Now, check out right here what an alpha particle is. So when we say some type of radioactive isotope undergoes alpha decay, that means that it's giving off an alpha particle. That's that's one of the products. We're going to do some more of these in just a second. And again, don't forget, there's always some energy given off. What is an alpha particle? Well, you can either write the Greek symbol for the letter A, that's alpha, or you can write the symbol for helium. So an alpha particle is actually a helium atom. Beta particle, it's a high energy electron, and the symbol is the Greek letter B, or you can use this symbol. And I should say, you guys, I prefer, and you'll see why in just a little bit, I prefer that you actually use the symbols. It will help you when we do the balancing of nuclear reactions, which is actually much simpler than balancing from chapter 5. It's just some basic addition and subtraction. It's really simple, but you really need to use the full symbol with the number on top and bottom to help you with the math. So that's what I prefer. That's what I recommend. But again, if you were given the symbol, B, like a Greek B, what in the world is that? Well, it's equal to an electron. Electrons have 0 mass. They are massless or essentially massless, and this is their charge. So if something is said to undergo beta decay, what that means is, again, you've got some kind of radioactive isotope that very unstable, and it wants to become stable. How does it become stable? If it was undergoing beta decay, it would release a beta particle and energy and form a more stable isotope. And again, we'll look at some of these in just a second, but just kind of going through the terminology. Then we also have beta particles that are made when you take a neutron. Neutrons have no charge, but have a mass of 1. When a neutron, this is crazy, when a neutron is converted into a proton and an electron. So, up until the nuclear chemistry chapter, you're taught that, you can't take one element and convert. I can't take carbon and make it hydrogen, or I can't take carbon and make it nitrogen, or whatever it is. Carbon is carbon. That's the simplest of all matter. But in truth, if we are dealing with nuclear chemistry and these crazy unstable isotopes and nuclear reactions that can be done in labs, we can actually take, for instance, even this subatomic particle, a neutron, and basically what happens is it gets bombarded with another little tiny particle. And we can do crazy things in nuclear chemistry that we never thought were possible. Our next type of radiation is what's called a positron, and just kind of in the name you see the word positive. And basically it's as it says, the opposite of a beta. So betas were electrons with a -1 charge and no mass. A positron is an electron with a positive charge. We call it a positive electron. And again, some radioactive isotopes undergo positron emission or positron decay. So again, as they're trying to form that more stable isotope, they release a positron in getting there. We can also make positrons, as you can see right here, taking a proton and converting it into a neutron and positron. Again, kind of crazy to think about. And then our last type, which is so I kind of went from least dangerous to now this is the most dangerous. Most penetrating. And that's a gamma ray. And it's a high energy radiation, again, given off by some radioactive isotopes. Okay, gamma is what happens in an X-ray. And everybody's been to the dentist, right? And what happens when the dental assistant or the hygienist wants to take an X-ray of your mouth? They put the lead apron on you. They usually have a lead apron on, or maybe they don't, but they walk out of the room because that's what you need. You need lead, you need like 6 inches of concrete. That's what will stop a gamma ray. Your clothing won't, a wall won't. You need something very dense like lead or a concrete wall, okay? And it's a form of energy, that's all it is. There's no mass to it, there's no charge to it, and so you won't see that there, you'll see there's no symbol over here with a number on the top and a number on the bottom, because that's not what it is. It's truly just energy. And this is the Greek letter for gamma, or the Greek letter gamma. Okay, so those are the type. Here's kind of the summary table. Keep this handy. If you get a problem that says, uranium-235 undergoes alpha decay, write the reaction, you can go look up, hey, what does alpha mean again, and find it, okay? Now, again, we're leading to balancing these equations, which is pretty simple. We'll get to that in just a second. So we know radioactivity can be very, very dangerous, right? It can kill human beings, it can kill cells, it can make people very, very sick, but it's also used, as we know, in medicine to kill cancer cells, right? It breaks their walls with all the energy, and you have to be careful, you know, if you have radiation, they direct the radiation treatment. Let's say I had, you know, like thyroid cancer or something. The radiation would be directed at my thyroid, and I wouldn't want it directed anywhere else, because not only will it kill cancer cells, it will kill healthy cells as well. So a lot of people get sick when they have radiation, because it sometimes, especially if you're, you know, having something irradiated like in your esophagus or stomach area or your throat, because it kills some of those cells as well, but they focus it on the cancer. Food is also irradiated, which I think is a good thing, because it kills any living organisms that are still in that food before you consume it. So we don't like that. The food itself is not radioactive, okay? It's just, it kills those organisms, and it gives it a longer shelf life. So, all right, so we're gonna look at these equations. And again, I promise you, these are so much easier than when you learn to balance in chapter 5, so much easier. Little addition and subtraction and you're good. So the idea is simply law of conservation of mass. So the mass on your reactant side and the charge has to equal the mass and the charge on the right-hand side. And you'll see what I'm gonna get here in just a second. So we've got these equations. All right, let me focus on this, okay? So this one's already balanced. I'm going to show you what I mean by the mass and the charge has to be the same on both sides. You know, I can't have a mass of 238 on the left and a mass of 240 on the right, because you'd go, well, where'd the extra mass come from? So the top numbers on the left and the right of the arrow, when I say left and right, that means of my equation, reactant left, product right. The top numbers have to be the same or add up. If there's multiple things, they have to add up to the same number. So you can see that on the left-hand side, the top number is 238. This is uranium 238. So on the right-hand side, my top numbers, 4 plus 234, has to add up to 238, and it does. But be careful, you don't just want to look at mass, you also want to verify that the bottom numbers also equal the same. And you can see on the left, the uranium has an atomic number of 92, nothing else on the left-hand side, so that's it, 92 on the bottom. On the right-hand side, helium has an atomic number of 2, and thorium has an atomic number of 90. So 90 plus 2 is 92. So 2 things you have to balance, the top and the bottom. That's it. So this one is balanced. Whoops, and you can see I didn't say this. Do you guys see here it says it's an alpha emission. So this would be an example of an alpha emission or alpha decay of uranium-238. Uranium-238 is a very unstable radioactive isotope. If they're stable, they're not going to do this, okay? So they're unstable radioactive isotopes. It's just kind of wild and crazy, and it wants to react so badly, becoming a more stable isotope. And so it does. It releases an alpha particle, which is a helium atom, and some energy associated with it, not to the level of gamma or anything like that. And what's left, when I basically pull out the components of a helium atom from uranium, what's left is thorium-234. All right, so how do the problems usually look that you would get in terms of this? You know, sure, I just gave you an example and said, yeah, this is balanced, and I showed you it was balanced, but how do you balance one that is like this? This is the much more common. You'll have a reaction like this on sapling, and there'll be like a big question mark. What goes in here? So again, the idea is simply addition and subtraction. The top on the left is 234. So the top on the right, again, left and right is of the arrow. So the top values on the right has to equal 241. Actually, let me make it red so it's a little more obvious because blue is the other color. So the question is, what plus 4 will equal 241? Well, let's just subtract 4. And it's something with a mass of 237, right? 237 plus 4 equals 241. Now we've got to do the exact same thing with the bottom number. 95 is what it needs to add up to on the right-hand side. And so far, I just have 2. So 95 minus 2 equals 93. So the bottom number must be 93 because 2 plus 93, yes, that equals the 95 that it needs to be. Now what do you do? Well, I've got one thing left, and that is, what's the symbol? What element is this? How do I know that? Well, you take the atomic number and your periodic table, and in fact, I've got to be honest, I don't even know what it is. I got to look it up. Neptunium. They tend to be the guys at the bottom of the periodic table that do all this stuff. So I go to the periodic table and I find out that NP, Neptunium, is the element with the atomic number 93. So step 1, do the math like we just did. Figure out what your top and your bottom must be. And then step 2, go grab your periodic table and find out what has the atomic number equal to the bottom number. You never want to take the top number and go searching, because this whole idea, what we're talking about, different elements have different masses. So there can be different elements with a mass of 237. And in fact, I don't have my periodic table right here, but Neptunium may or may not even be close to 237 on the periodic table. This is what forms, though. And so you decide what you have, all based on this bottom number. That's the identity of the element, just like your social security number identifies you. Excuse me, not your mass. Okay, your number identifies you. Do the math, go to the periodic table, look up and see what it is equal to, what has that atomic number. That's it. Okay. Here's a beta emission example. Now I just want to show you this one because, again, the same idea applies. My top numbers and my bottom numbers have to be the same on the left and right hand side, but be careful when you have a beta particle, which is an electron, you have a -1 on the bottom. So on the left hand side, I have 6 on the bottom. On the right hand side, I have 7 minus 1. 7 minus 1 equals 6. So when you have a beta particle that's released, you have to use the -1. Or if it's a positron, you use +1. But watch your numbers, okay? It's still addition and subtraction. And again, the top 14 is your total on the left. Electron has a mass of 0. So 0 plus 14 equals 14. Okay? And then here's the example with the positron. Okay, positron right there. It's an electron, so it's still 0 mass, but positron means it is positive on the bottom. Again, mass has to equal. So I have 6 on the left. I have 5 plus 1 is 6 on the right. I have 11 on top on the left, and 0 plus 11 is 11 on top. So this is also balanced. And then what do we do with gamma? There's no numbers for gamma. There's no numbers for gamma. Well, so typically what you'll see is that on the reactant side, when we have an element that's going to undergo gamma decay, meaning giving off gamma rays, we say they're gamma rays, which is just energy. Typically what you'll see is there's the letter M next to the atomic number. And M, as it says here, means it's a metastable isotope. And that distinguishes technetium-99 on the left from technetium-99 on the right. You go, well, what's the difference? They're both technetium-99. Well, on the left, on the reactant, this is your very, very unstable one. And it's, again, like just looking to react. And once it releases and gives off that gamma energy, it forms the more stable technetium-99. So the M just means unstable before it has done its thing, releasing the gamma, and without the M, that's just as where it's at. Okay, now as it says here, interesting is there can be multiple radioactive particles, gamma energy or gamma rays. There can be multiple things happening within the same reaction. The math and everything still adds up to the same. You won't see, however, notice for cobalt 60 here, there's not an M there. Well, that's because I didn't form cobalt on the right. So I don't need to distinguish between before and after. And the reason it didn't form cobalt on the right, even though gamma was released, is because, again, this was a multi-emission process. Not only was gamma emission occurring, but a beta particle was also given off, okay? So again, let's do our math. I've got 27 total on the bottom, on the reactant side. I have 28 minus 1, and gamma has no numbers with it. So 28 minus, whoops, it's not 0. 28 minus 1 is 27, and that matches over here. And then at the top, I have 60 on the right, 60 on the left. I have 60 plus 0 from the beta particle, and gamma again has no numbers, so 60 plus 0 is 60, and that equals what it was supposed to be on the top on the left. So my numbers all balance, even if it's multiple emissions. Okay, so balancing nuclear reactions is usually a fairly easy thing. Now I will say one other thing, hang on, let me go back to this. Sometimes you'll get multiple. Let's say, for instance, let me give you an example here. I'm gonna have to grab my periodic table. Let's say, well, I'll do carbon 12. Let's say you have carbon 12 that's decaying into, I don't know, you're supposed to figure it out, plus 2 neutrons. So let's say this was your radioactive equation that you have to figure out. What's the question mark? What's this guy right here? And this is what you're given. So this is carbon 12 decaying into something we have to figure out, plus 2 neutrons, plus 2 neutrons. I wanted to do this one to show you that there can be more than one of your particles, okay? But you have to be told that. You guys would never know that. We're not learning, you know, why some do that multiple and some don't, okay? It's just, if you're told there's 2 neutrons, you simply apply the number 2 to the math. So on the bottom here, I have 6, and here's my eraser here. I need to figure out the bottom number, and I need to figure out the top number of my unknown. All right, so 6 is the bottom. 6 is what we're going for, left and right on the bottom. But if you notice right here, the neutron has a mass of 0. It has a mass of 0. So this is still 6. 6 plus 0, even if it's 2 times 0, even if there's 2 of them, it's still 2 times 0 is 0. So the mass is 6. Excuse me, not the mass. The atomic number is 6. And then the top, let's look at the top now. The top needs to be 12 when I look at the left and right. Now, you know, again, what's going to go in my blank space right here? Well, I got to do the math and figure that out. I have 2 times 1. 2 times 1 is 2 coming from the neutron. And it needs to add up to 12. So 2 plus what equals 12? 2 plus 10 is 12. So I would put a 10 here. Now my question mark I can now replace, in fact I could have done it after the last step, I can now replace with a symbol, because all I need is the atomic number and my periodic table. Find out what has atomic number 6. 6 is carbon. So this would just be another isotope of carbon. Mass of 10, atomic number of 6. Okay. All right, half-life. So let's talk about half-life. This is probably the most difficult part of the chapter. I'm going to try and make it pretty simple, at least I hope for you. So half-lives, the amount of time it takes, half-life is a time, okay? How much time it takes for the original radioactive isotope to decay halfway. So the example right here, if I start with phosphorus 32, and I'm starting with 16 grams of it sitting here in my hand, how much time does it take before, it's all gone or it reduces, right? Because it's giving off radiation, it's forming new substances. It looks like it's forming sulfur 32. Well, the half-lives, again, have to be given to you. It looks like the half-life for phosphorus 32 is 14 days. So what that means is every 14 days, the amount of phosphorus 32 that I have gets cut in half. And in fact, if we wanted to look at the reaction, it's forming sulfur with the same mass of 32. It's giving off, I don't know what is it giving off an electron, something like that. We don't have to do the equation. But again, it's not that it just magically disappears. Phosphorus 32 is the unstable radioactive isotope reactant, and it's decaying, whatever it does, beta particle, alpha, whatever it is, it's decaying and producing a more stable, looks like sulfur 32. I just know that because I'm looking at the slide and it says that. But notice what happens after the 14 days, the half-life, 16 gets cut in half. I have 8 grams of the phosphorus 32, the original, still there, still wanting to react and decay, and I've produced 8 grams of the product. And so the totals, 8 plus 8 is still 16. The totals always have to add up to the original. Again, the law of conservation of matter says matter isn't created or destroyed. It can be converted, but it can't be created or destroyed. So 16 gets cut in half and goes to 8 after 14 days. That's the half-life of this particular substance. Another 14 days goes by. So this would be after the first half-life. This would be after the second half-life. Another 14 days goes by, or a total of 28 days. Now I only have 4 grams of that unstable stuff left. A third half-life goes by, another 14 days. 4 gets cut to 2. And I could keep going until I have nothing left. After another 14 days, a third half-life, I'd have not 2 grams, but 1 gram. So every 14 days, the amount of that unstable radioactive isotope gets cut in half until there's nothing left and it's all been converted into this stable product. Okay, so people think half-lives, like a lot of students just think, oh, after 14 days it's cut in half and it's done. No, it keeps going. It's just that's how much time it takes for it to cut in half. And every 14 days in this instance, the amount is cut in half, and cut in half, and cut in half until you got nothing left. Here are some interesting half-lives of different things. Again, you don't have to memorize this. You'd have to be told half-lives or be told to go look it up. Some substances have really long half-lives. And in fact, carbon-14, you've probably heard of the term carbon-14 dating. They use that in artifacts. They find something that's really old, like a fossil, and they measure how much carbon-14 is still left, and they work backwards to how much should be in there in a living being, how much carbon-14 should be there, because we are exposed and breathing in minute quantities of carbon-14. And they look at how much it actually has when they find it, and knowing that it's 5,730 years for it to be cut in half, they can figure out what the age is. A lot of these other ones are all used in medicine. In fact, they all are. Cobalt-60 is for cancer. Iodine-131 is thyroid. Oh, potassium, I guess, is it? I thought that was maybe used for something with the heart, but phosphorus-32 for leukemia, technetium-99M, that metastable version, organ imaging, nuclear reactors use uranium-235. That's what they're using at the Byron power plant right now, is that unstable. So lots of things used in lots of different ways. It's really quite amazing. And you can see the half-lives vary. And I always like to tell this story about iodine-131. My college roommate and I totally, this was a total like by chance freak thing. Her and I both at the same time had tumors in our thyroid. And we went home. I don't know if it was spring break or summer or something. But we really just didn't talk. I mean, we were both going home and getting treatment. So, okay, it was what it was. I went home, I come back, I have this huge bandage on my neck. My neck's been sliced open and they took out my thyroid with the tumor. She comes back and I remember getting to our apartment first and getting all settled, and my mom came back and got me all settled. And then she comes in and she's like bouncing off the walls and like nothing's wrong with her. And I said to her, Megan, I'm like, oh, you didn't have your surgery. Now remember, we didn't have cell phones back then, or we didn't have cell phones. So, and there wasn't really email. So you just talked on the phone or you didn't talk, so we didn't talk over break. Get back. I had surgery. She had nothing. And I was like, what's the deal? What happened? And she's like, no, I had my thyroid's gone. And I looked at her neck and I said, well, why don't you have this massive incision and bandages? And how in the world? She's like, oh, well, they did the iodine 131 treatment on me. I went, what? I didn't get that option. They cut me open. Well, what happened was they gave her iodine 131. Our thyroids process iodine that we consume. Now, normally it's not radioactive iodine in our diet, for instance, but your body doesn't know and your thyroid doesn't know if it's iodine stable or iodine radioactive. So you take iodine 131, I don't remember if it was an infusion or a pill, I don't remember. But basically when your body sees the iodine, it says, hey, iodine's here, send it off to the thyroid for processing. And regardless of what kind of iodine it is, it goes to the thyroid and the thyroid processes it. Well, you can see the half-life. So basically the iodine that they gave her went to her thyroid and it was radioactive. It was sitting in her thyroid being radioactive, giving off energy that was killing the cells of her thyroid. Now, normally you wouldn't want to do that, but they wanted to kill her thyroid, get rid of her thyroid. For me, they cut me open and took it out. For her, they used nuclear medicine to basically irradiate it. And so what was really cool, because then we started talking and it's like, again, I was just starting we were both just starting in college, so we didn't know a lot about anything with science yet. But we were talking and I'm like, well, so what happens? And she said, well, I went in the hospital and I was there for 3 days. And I said, you were, but you didn't have surgery. She said, no, they put me in a room and basically I was in isolation so that I wasn't exposed to other people because again, after she had that radioactive iodine 131 treatment, she was giving off radiation and they don't want you exposed to, especially like little kids. So they just had her hang out at the hospital and she said it was almost like she was in prison. They'd bring her meals in, slide it under the door or whatever, put it through the door. And she really wasn't around many people and she just watched TV for a couple of days and hung out. But again, it has a relatively short half-life. So after a couple of days, the amount that's still left in your body is such that you could then be around some other people. They did tell her, I think for like a week, she wasn't supposed to be around little kids. So anyways, that's my side story I always like to tell about iodine treatment. I had mine cut out and she had hers. Okay, so let's look at some problems with half-life. And again, I'm going to kind of just explain my way of doing these things. So it says, if the half-life of the iodine 131 is 8 days, how much of a 100 milligram sample would remain after 32 days? All right, so the first thing is, okay, they want to know after 32 days. Well, every 8 days, it gets cut in half. So 32 divided by 8 says, okay, the amount's going to get cut in half 4 times. So if I start with 100 milligrams, after the first half-life, which is 8 days, there would be 50 left. After a second half-life, 8 plus 8, now I'm at 16 days. There would be 25 milligrams left. I'm still not at 32 days. After a third half-life, 16 plus 8, after 24 days, I have 12.5 milligrams left. And I'm running out of space because I wrote too big. Let me just come down here. And after a fourth half-life, 24 plus 8, there's my 32 days. 12.5, cut that in half, 6.25 milligrams. Now, that kind of seems like a long way to do it. I'm just using the idea of understanding what half-life is, that it's cutting it in half, and I just keep adding up the time until I reach my goal of 32 days. Now, the way that I show you on the slide's a little different. You figure out how many times exactly you got to cut it in half, and then look what you do. You cut it in half 4 times. We did that. I just did it each time. I took 100, went to 50, went to 25, went to 12.5, and then went to 6.25. So you're doing the same thing, okay? So figure out how many times you're going to cut it in half, and you got your answer there. Again, carbon-14 dating I've talked about. I'm sure you've heard at least the term. They're comparing how much carbon compared to a living organism, a plant, a human, should be in there versus how much is in there when they find it. Because once an organism, a human or a fossil, a plant, whatever, once it dies, respiration stops. So the input and output of carbon, breathing it in or exhaling carbon dioxide, that stops. Or if you're a plant, photosynthesis stops. So the amount of carbon, basically you're just putting a clamp on it, like, hey, it's going to stop. But radioactive version or form, which is only carbon-14, carbon-14 is able to be measured then, as it says here, comparing the ratio of carbon-14 to carbon-12 in an artifact to the same ratio present in something that's here today, figures out what the age is. And again, the cool thing is because carbon-14 has a really, really long half-life, we can date things back millions of years, okay? If half-life was 1 day, we wouldn't be able to do it, but it's a huge half-life. Now, in terms of monitoring, the amount of radioactivity in a sample is measured by the number of nuclei that decay per unit of time. And that's considered, or what's called a disintegration per second. And the unit, the most common unit that we use is called the Curie, named after my cat, Madame Marie Curie. Actually, no, my cat is Madame Marie Curie. But I named her after the famous scientist, Marie Curie. Marie and her husband were fascinated with nuclear chemistry. And in fact, they were the inventors of the X-ray. Now, the sad story is they didn't realize the damage that it was doing. And Marie was the guinea pig. Her husband would take the X-rays of her over and over and over. And she was X-rayed literally to death. She was exposed to so much gamma radiation through all those X-rays that she died of cancer. It's terribly sad. Anyways, but she's so famous, and I'm so grateful for all of her work, and we've named this particular unit after her. And you can kind of see, what it is. 3.7 times 10 to the 10th disintegrations per second. That's huge. It's disintegrating really, 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 really fast. We can also do millicuries, which just works like milliliters. 1 base unit equals 1,000 milliunits. We can also do micro, which is 1 base unit equals 1 times 10 to the 6th micro units. Or we also have Marie's husband, Henry Becquerel, have that as a unit as well. So anyways, different units. We don't do a whole lot with the units and actual measuring, but it is important in terms of then measuring how much is absorbed by an organism. So RAD is the radiation absorbed dose, RAD. It's the amount of radiation absorbed by 1 gram of a substance. But what we typically see for humans is this REM, radiation equivalent for a man. That's how much radiation that factors in its energy, and then what's most important, damage to our bodies, to living tissue of a human. And it says 1 rem of any type of radiation produces the same amount of tissue damage. So the rem is not specific to the type of radiation, it's specific to the danger and damage that it does to our bodies or to living tissue. So interesting facts here. The average radiation dose that we're exposed to primarily comes from the sun, but we're exposed to about 0.27 REM a year. Really, that's not usually detectable in terms of the effects. Anything less than 25 is usually you would never know it. But let's talk about when you would know it, or when you're exposed to too much. If you get a single dose of 25 to 100, it can cause a temporary decrease in your white blood cell count. Again, people undergoing radiation, where they have more than a single dose, unfortunately. But they tend to have, they're at high risk for, picking up colds and viruses and terrible things. Their white blood cell count is low. If you're exposed to a dose greater than 100, then you are exposed to and typically have radiation sickness. Again, you've heard of that, and you've heard of probably some patients or friends or family members that have had some sickness like that. And then, worst case here, the LD50, the lethal dose that kills 50% of humans. And it's all the way up at 500 rem. So if you were exposed to 500 rem of radiation, you have a 50-50 chance of it killing you. And then go from 500 up to 600, and it's a 100% fatality. If you guys haven't watched Chernobyl, it's a really, really good. Was it on Netflix? I think it's on Netflix. I watched it a few months ago. Maybe it's not on Netflix. Maybe it was. I don't know. But it's a really good. I think it was like 6 or 10 episodes. It's called Chernobyl. You should watch it. It's really interesting. It's supposedly based on the Chernobyl incident in Russia, when the radiation incident happened there, and lots of people died. People got sick. It was terrible. So in terms of medicine, I talked about a little bit ago with like the iodine 131 and my college roommate. Again, I can't remember if she was injected or if she was given a pill, but either one, basically you consume it somehow. And low doses can be used for organ function testing. So even to look at your thyroid, sometimes you're given a very small dose of iodine 131 because, again, your body gets iodine, it sends all the iodine to the thyroid. And so at a small dose, you take iodine, then you have a scan done, and it will light up your thyroid, and you can see is the thyroid processing the iodine? Is it processing it through? Again, you'd want to do a low dose because at a high dose, you're going to kill off the thyroid. Technetium 99M is used to evaluate like the gallbladder because, again, this would be an isotope or an element that when the body sees it, to the gallbladder for you. And then that's where it gets processed. Thallium 201 is used in stress tests to diagnose coronary artery disease. And then again, using a scan, normal organs are clearly visible, malfunctioning or obstruction ones are not. And here's a picture. So this is, you can see what we were just talking about with the technetium 99M. It was given to a patient, and then they're assessing through a scan the liver, gallbladder, kind of bile ducts. It appears. Remember, the rule is if it appears, that means it's good. It's going and where it should go. It's being processed properly, so it's lighting up, and I can see the outline, of the organs here. Some different some different isotopes for different things. I talked about the technetium and the iodine. Here's just some other ones. And again, it's all based on what our bodies do when it's exposed to, whether it's injected or ingested, different elements. Xenon would go to the lungs. Technetium can also be used in bone scans. It can be used in gallbladder. Technetium is a pretty common one. Iodine I talked about for thyroid, phosphorus 32 for leukemia and lymphomas, iridium, cancer of the breast, and then thallium for heart function. So different isotopes for different things. You may have heard, or maybe you know someone that's had a PET, or maybe you've had a PET scan, which is positron. Now we know what a positron is, right? Here's what a positron is. So there's what the P in a PET scan means. Positron emission tomography. So it uses radioactive isotopes, which are giving off those positrons, and the scanning can then pick those up. Can detect all sorts of things. It's non-invasive, so we love these scans like MRIs and CAT scans and PET scans, because before that, they'd have to open you up if they wanted to see, if you had something going on. And so the scans are all considered non-invasive. Even if they have to, hook up an IV and inject you with something, that's still considered non-invasive. You're not going to be cut open. And here's a PET scan. You can see they're looking at the kidneys and the bladder on the left. That's good. You can see it all lights up, you know, everything happening. And on the right, you can see this is all not happening here. So that's not good. All right, and then kind of the last few things, you guys, nuclear fission and fusion. So these are the two nuclear reactions that are involved with massive quantities of energy. This is what's happening at the Byron power plant that generates so much energy that we can power our homes, you know, and cities and towns are powered. So fission is the splitting apart. You have this big, massive uranium-235, and it's bombarded with a small, tiny little neutron, and it begins to decay when it gets hit, and it forms smaller things. Fission is the breaking apart of something big into something smaller. And again, you can see it's the krypton, the barium, and then in fact here you get 3 of those neutrons, which then can go on and bombard more uranium even. And again, the kicker is it releases great deals of energy. Great deals of energy. Let's see. Oh, the chain reaction, yeah. So for this is the same reaction here. These 3 neutrons that are produced can go on and bombard other uraniums. It creates what's called a chain reaction. So you only have to start with 1 neutron. You hit the uranium because it produces 3. It's a 1-to-3 ratio. You need 1 and it produces 3. Those 3 go off, hit more uranium, and it's just this chain reaction effect. Critical mass, that's just a term we use, the minimum amount of uranium or any radioactive isotope needed to sustain a chain reaction. So what that means, if I just have 1 atom of uranium-235 and I hit it with a neutron, sure, 3 neutrons are produced, but there's no more uranium-235 for those 3 to hit. So you've got to have a substantial quantity for this massive chain reaction, which is where you get the crazy amounts of energy. You've got to have a minimum amount of energy or minimum amount of the radioactive isotope to do that. It's called the critical mass. Again, fission's what's happening in power plants. What happens is the energy that's produced is used to boil water. The water, liquid water, turns into water vapor or steam. That turns a turbine, and that turning of the turbine, if you think about like the wind turbines, you've seen those, we've got those in Illinois. When those wind turbines turn, it can generate electricity, and then that's where we get our power from. Problems and dangers, of course, with nuclear power, possible radiation leaks, and where do you dispose the waste? We haven't had any big issues here in the United States ever. I talked a minute ago about Chernobyl. Again, if you don't know anything about Chernobyl, look it up. It is an amazing story of a nuclear power plant gone very, very wrong back in the USSR. I think it was in the early 80s when it happened. I remember it. I was a little kid. In the United States, our plants have been very safe. We had one near incident. It was in Pennsylvania at the 7 Mile Island, where they thought they were going to have a radiation leak, but they were able to contain it. And they actually evacuated people. My ex-husband lived there at the time. He was a baby, but his mother tells the crazy story of them being evacuated and everything. So of course, again, risk of radiation. If something bad were to happen at a nuclear power plant, it would be bad. Okay, but for the most part, especially in the United States, again, we have such tight regulations. I feel very comfortable living, you know, I don't know how far I am, 10 or 15 miles maybe from Byron. I wouldn't mind living, you know, a mile from it. I think I feel very comfortable with it. I think it's a cleaner source of energy compared to fossil fuels, my personal opinion. And then the other part of that, nuclear waste. What do we do with all the waste left over when they have these spent fuel rods where the uranium-235 is? Right now, most of it is shipped out to Nevada, to the middle of nowhere, to this place called Yucca Mountain, and they bury it. Now, for a long time, that seemed to be just fine, no problems. However, in reality, you know, there's groundwater, and there may eventually be people that live there. So there's a lot of question on whether that's safe. Some people want to put it out in the ocean, but again, obviously that would be, you know, exposed to, you know, organisms and things in the water. So, but again, so those are the two big controversial and serious issues that have to be addressed with using, again, fission processes in nuclear power plants. The opposite of fission, splitting apart of big things, is fusion, and that is literally fusing together something. Fusion is fusing. Everybody knows what fuse means, right? Merging together. So fusion is when you take a couple little things and you put them together and make something bigger. Fission, a big thing becomes smaller. Fusion, little things become bigger. So you take, for instance, hydrogen 2 and hydrogen 3, deuterium and tritium, and you make helium, make an alpha particle and a neutron. This also, insane amounts of energy. This is what's happening on the sun, for instance. Huge amounts of energy, okay? It'd be great to be able to harness some of this energy and do things like, operate cars, but it can only happen at extremely high temperatures and pressures. It's just not realistic to happen, especially to do something like power your car with. So that's it. You guys, that's it. That is chapter 10.
Thank you.
You're welcome. You guys have any questions or anything for me?
Can I ask you a question on our homework for chapter
Sure.
10?
Mm-hmm.
Okay, so we have a balancing an equation question that I don't understand.
Okay. Do you
I can show you.
Can you want to show me your thing?
Here, I can show you it. Yeah, let me flip my screen.
Oops.
How do I flip this?
You could even do a screen share. Do you want me to let you screen share?
Well, I'm on my phone. Okay,
Oh, okay,
that's
there we go.
balancing the equation.
Okay,
But
wait. So it's kind of, so it's AL. I'm trying to read what's on the left. AL
27
7
plus 4 HE.
Yep. Makes
2.
1 neutron.
Yeah.
Okay, so let's talk about what we just did. So the top numbers on the left and right of the arrow have to add up to be the same thing. So when you look at the reactant side, tell me what those numbers add up to.
So the 27 and the 4?
Yep.
31?
Yep.
I don't know. Is my math off?
Yep.
Today?
No, that's right. No, that's right. 31. And so, okay, on the right-hand side, you've got 1 neutron that has 1. So 31 minus 1, the top number needs to be 30.
30. Okay.
Now the bottom number, well, they were kind of tricky and they didn't give you the atomic number, but I can tell you aluminum is 13, helium is 2. So the bottom numbers, and just because they didn't give it to you again because aluminum is always 13 and helium is always 2. So technically they don't have to give you the bottom numbers, but you're gonna need your periodic table. So aluminum is 13 on bottom, helium is 2 on bottom. So the bottom total has to be 15.
Okay.
Well, okay, on the right-hand side, you have a neutron that has a bottom number of 0. So 0 plus what is 15?
15.
Right, it's not a trick, it's 15. So you take that number 15 and you say, okay, periodic table, what element is number 15? And it's phosphorus.
Okay, so I think I was doing it wrong because I wasn't putting the bottom number.
And I don't know if that problem once, like, I'm not sure, you really shouldn't technically have to put the bottom number because they didn't put it, but, and it's always 15, but maybe they want the bottom number. I don't know.
Yeah, because I tried it like 7 times today, but now that I just put a bottom number, it works.
Oh, okay. Well, that was tricky of them. They should have put bottom numbers on theirs then if they wanted.
I was so confused. I was like, what am I doing wrong?
Yeah.
Okay.
Is that good? Okay.
Yeah, just that one is the only one I was confused on.
Okay. So let me show you everybody else so they can kind of see, because you and I just kind of scribbled through that really quick. Let me go back and show you, just because I have a minute here. Since we're done, let me screen share and kind of explain what we just did. Let me go back to my iPad share. Okay, so here was her question. Her question was this. She had 27 Al aluminum plus 4 helium makes, and she had like a box here, the unknown, plus 1 neutron. That's what the problem gave her, okay? And so what we were talking through was what goes in the box. Well, first thing that I would have done, because you're going to need it anyways, I'd go fill in Let me change it to a different color since I'm writing this. I would go look up the atomic number for aluminum, and I'd go look up the atomic number for helium, because I'm going to need to know what those bottom numbers are too. And what I was saying a minute ago was the reason the problem didn't give them is because aluminum is always 13. Helium's always 2. It's the top numbers that can vary. Again, the top is the mass, the bottom is the number. So my mass can change, can be different, but my number is always my number. So they didn't give that to us, but we're going to need it. And so it doesn't matter which one you start with. I'll start with the top. So the top on the left-hand side is 27 plus 4, which is 31. On the right-hand side, I have right now just 1. So the question is 1 plus what equals 31? Well, 1 plus 30, right? And you could always go back and check yourself, you know, okay, I put 30 there, 30 plus 1, yeah, that equals 31. Okay, and then we're going to do the same thing on the bottom. I have 13 plus 2, which equals 15 total on bottom. And on the right-hand side, I have 0 from the neutron. 0 plus what equals 15? Well, 15. That was what I said. It wasn't a trick question. So now what do? You always do the math first. You have to. Then you go grab your periodic table and you look up and see what has atomic number 15. You can't look at the mass because it doesn't always match. Again, the atomic number on the mass on the periodic table is an average based on abundance and isotopes and all sorts of things. So you can only look at the atomic number. And what has the atomic number 15? And that's phosphorus. Okay. Does that make sense?
Yes, thank you.
You're welcome. Anybody else have anything else?
Nope.
All right, you guys. Well, that is it. So you guys, you can take your exam anytime between now and next week. I can't remember. Let me look and see what time when the cutoff is. I don't remember. I have to look. I think I just set it for when our class normally ended.
Yeah, it's May 15th.
Okay.
Yeah.
So you've got through May 15th to take that last exam. I still am dropping your lowest one exam score. So that's it. That's all you've got left.
All right.
Oh, I guess you have chapter 10, excuse me. And chapter 10 is due this Sunday. So hopefully now with this lecture that helps you. Homework chapter 10 and then your last exam. All right, you guys. If you have any questions, you know, send me a message. I had a great semester, even though it was so strange. You guys. So best of luck in all your classes. And again, if you need anything, just let me know.
Okay, bye.
Thank you. Bye.